Okay. Hello, everyone. My name is Kyohan Kang, and I am from the Spatial AI and Robotics Lab at Ina University under the supervision of Professor Younggun Cho. Today, I will present my work on a unified mapping framework for multimodal LiDAR in complex and dynamic environments. First, I will provide a motivation for our work. In construction site, the deployment of robot automation necessitates large-scale, high-precision mapping. Moreover, as construction progresses, there is a need for method updating the map temporally. These kind of problem require solutions such as multi-agent collaborative SLAM or multi-session mapping. Among the various sensors for mapping, LiDAR have become highly favored sensor due to their accuracy and extensive coverage. Recently, advancements in LiDAR technology have led to the development in diverse types of LiDAR sensor. This expanded the range of LiDAR that construction robots can choose, which can vary in each size, operation mechanism, scan range, and more. However, different types of LiDAR sensor and POV result in significant variations in the distribution of LiDAR point cloud data. Specifically, LiDAR sensor has its own vertical and horizontal field of view along with unique scanning patterns. Furthermore, the point cloud can also vary based on the robotic platform and the mounting of the sensor. Such variability can hinder LiDAR place recognition, which is a critical component of map merging. Moreover, dynamic object prevalent in construction sites create a ghost trail effect during mapping. And it degrades the performance of map fusion in place recognition and registration as the point cloud of dynamic object exists transiently. So our goal is to develop a map merging system that is robust to LiDAR modality and dynamic environments for multi-session and multi-robot scenarios. Therefore, our contribution shows as follows. Before introducing our method, this figure presents an overview of our framework. Initially, our map merging system is modular, allowing the use of any odometry estimation algorithm. After pose estimation for each frame, our system comprises two main modules, dynamic aware scene description and multiple pose graph optimization. Pre-existing methods such as scan context or reach variations are based on projecting scan measurement to extract descriptors. However, construction environments often deal with extreme elevation changes and narrow spaces, which require detailed descriptor that can efficiently represent the 3D space. Therefore, we have developed an automated pipeline that integrates dynamic object rejection and stable triangle descriptor called SCD, which is the state-of-the-art LiDAR place recognition algorithm. First, dynamic remover detects dynamic objects through free space estimation. The key idea is to estimate the ground region at the voxel level and designate free space as vacant region between ground and the lowest non-ground voxel. Using a coarse-fine approach, it performs adaptive voxel analysis and detects dynamic object based on a sliding window and a recursive binary base filter. After rejecting dynamic points, we perform scene description on the static point cloud. As STD consists of multiple local triangles, it facilitates loop detection across different types of LiDAR. However, dynamics act as outliers in formulating local triangle descriptor, and our dynamic aware STD enrich the structural encoding of the descriptor as shown in the yellow boxes. After seeing description of each map, all map data is then shared with the map merging server. We designate the central map as the base session for anchoring, which covers a wide area with numerous intra-session loops and utilize a LiDAR with a wide FOV to generate a rich set of local descriptors. Anchor node-based pose graph optimization is adapted to alleviate drift errors in single session odometry, and robust kernels are utilized to address false matching pairs. Before moving on the result of our framework, this table shows details of each data sequence we used for evaluation. In the heliport dataset, we use Town 1 and 2 sequence, which feature diverse urban environments, and our custom dataset INA for multi-robot system in our campus. All data sequence equip unique LiDAR types and have abundant dynamic objects. On dynamic object remover, our method demonstrates improved performance in AA score comparing with removert, which implied the overall performance of static map preservation and dynamic object remover without prior map data. Furthermore, our module shows computational efficiency being more than twice as fast, though the runtime of our method includes the time for scene description. In place recognition, global descriptor except STD variant struggle to handle cross-modal LiDAR place recognition. Integration with STD and dynamic remover demonstrate robust performance in dynamic environment and various types of LiDAR setting. Blue box on figure shows more true loop pairs are matched in maximum precision condition by rejecting dynamic objects. Finally, our map merging algorithm shows the best performance in ATE criteria in both helper and INA datasets. And this is our experiment video on our campus with 5 different robot platform and LiDAR types. We set central map as orange oyster session, and all maps are aligned well with removing dynamic objects. This is our final static unified map, and such red points indicate rejected dynamic points by our framework. So conclusions. We introduce a dynamic aware and LiDAR modality agnostic multi-map merging framework. We verified our result in multimodal LiDAR dataset and shows relatively better performance in LiDAR modality and dynamic environments in place recognition and map merging. However, recall rate of place recognition across heterogeneous LiDAR is much lower than that of homogeneous LiDAR. This is still an open problem, and helper could be a base dataset to solve this issue. Furthermore, our system only aligns multiple maps in central map coordinates. Further research such as extension to decentralized multi-agent SLAM or long-term map management like change detection would be on our future works. Thank you for your attention. If you have any questions, feel free to ask after this session or contact me. Thank you.
For the presentation. So